Today we're going to take a look at section 1.2. I don't know how good you guys are at recognizing patterns. Some of you are probably better than others. We're going to explore patterns a little bit today and on Friday as well. Patterns have a lot of power. We can actually do a lot of things with patterns. And so we're going to start by taking a look at a little bit of vocabulary regarding this. The first word, you've probably heard the word conjecture before. A conjecture is a statement or conclusion that has not been proven. People throw conjectures out like they're truth all the time. But if it's not been proven, then it's a conjecture. A counterexample is something that proves a conjecture false, at least in that example. And then there are two types of reasoning. One type of reasoning is called inductive reasoning. And it's a method of making generalizations based on observations or patterns. And then deductive reasoning is when you use mathematical axioms, theorems, definitions, or undefined terms assumed to be true, and logic for proof. So let me give you kind of just an example of the difference between the two approaches in thinking about it. They're neither one like maybe better than the other, and we use them all the time. So, for example, my daughter works a part-time job. She works in childcare. And she goes for roughly the same number of hours every day. She pretty much gets her out of school. She stays till they close and so forth. So if she's using inductive reasoning and she's saying, well, yesterday I got paid $25, and the day before I got paid $25, so today I'll probably get paid $25. That's inductive reasoning, right? She's working about the same number of hours. That's inductive reasoning. If instead she said, yesterday I worked 5 hours and my pay is $5 an hour, therefore 5 times 5 is 25, I'm getting paid $25. That's deductive reasoning. Do you see the difference? Right? There's a concrete formula that she's using instead of saying, this is what it's generally been, so this is what I expect it to be. So we're going to look at a lot of different examples of those in context of mathematics here in a moment. A few more definitions before we do, though. Sequences are an ordered arrangement of numbers, figures, or objects. Kids encounter sequences really young, like pre-K stuff. It'll say something like triangle, circle, what comes next in the sequence, right? Yeah. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given, and a rule that shows how to obtain each successive term of the sequence. So we looked at some homework questions back in section 1.1 with the dots in between, right? You know what I'm talking about? So there was one of them, the last one we looked at said 3, 6, 9, 12, 300. That's a recursive formula. You know, I add 3 to the last term to get the next one, and I add 3 again, and I add 3 again. So the rule is add 3, and I've got a few terms to start it out in my sequence. Okay, so that's a recursive kind of an idea. The opposite of that, or we'll say opposite, is having a general term. A formula used to find the nth term of a sequence with no prior terms needed. So that same one that I gave you, and actually I think I'll write it down to show the difference. Okay, would say that our value, let's see, E, is 3n. For n equal to 1, and so on. Well, 2, and so on. So if you wanted to know, for instance, the 10th term of the sequence and you had this formula 3n given, you would say, well, 3 times 10 is 30. That's the 10th term of the sequence. Okay? If you wanted to find the 10th term of the sequence with the recursive formula, you'd have to actually sort of count it up. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Right? There's my 10th term of my sequence. It's 30. I can still get there, but I've got to do it in this sort of a repeated patterning instead of being able to do it from a formula perspective. Both of them have their place, but they do things a little bit differently. A couple of different specific types of sequences we're going to take a look at. 3, I think, actually, between today and Friday. The first one is called an arithmetic sequence. This is a sequence in which each successive term is obtained from the previous term by the addition of a fixed number. That fixed number could be positive, it could be negative, it could be whole numbers. That stands for whole numbers. It could be fractions. So I'm going to put a Q. That stands for rational numbers. So if you want to write down whole numbers, write down fractions. It can be anything added to that value. All right? So if you had the sequence, 3, 2.5, 2, 1.5, that would be an arithmetic sequence because the added term is -1/2 every time. Okay? And we don't deal with a lot of them that are sort of not so nice looking. We deal with a lot of things that have whole numbers and so forth, but negatives are certainly a possibility too. This value that keeps being added is called the common difference. So in that example that we had before, 3, 6, 9 to 300, the common difference, we use the letter D, was 3. Positive 3 if you want to be real specific, right? We added 3, positive 3 every time. The other example that I gave out loud, where I subtracted the 1/2 each time, or added the -1/2, the common difference D would be -1/2. Okay? So we have arithmetic sequences. The next one are geometric sequences. So arithmetic sequences are an addition of a value. Geometric sequences are the multiplication of a value. So you multiply by a number to get the next number in the set. And then you multiply, and then you multiply, and you multiply. And again, this fixed number could be positive, could be negative, it could be a whole number, or it could be a fraction or a decimal or something like that. It doesn't have to be nice, pretty numbers, though most of ours will. But it could be positives or negatives as well. So, like maybe you had 108, 36, 12, 4, ... This is a little bit of a funny one because I want to show you one that's weird. The numbers are getting smaller. So you might think, but Dr. Hensel doesn't look like it's multiplying, it looks like it's dividing. You could think about that. Let's actually do that for a moment. What does it look like it's dividing by? Looks like it's dividing by 3, right? It looks like in order to get here, I divide by 3 each time. And it's okay to think about it that way. But eventually what you have to remember is that dividing by 3 is the same. I meant to put a 3 there. Dividing by 3 is the same as multiplying by 1/3. Okay? So it's okay to think of it as division as long as we still get to the point of, well, then what does that mean I'm multiplying by? Because there's always a multiplication factor associated when there's a division process going on. And when that happens, the common ratio, that fixed number, we call it R. In this case, it would be the number 1/3. And again, that R can be positive or negative. Most of the time, it's not going to be fractions, but it could be as we're working with these. There's exactly one more type of sequence we're going to talk about. And that one's called a Fibonacci sequence. So just with a show of hands, how many of you have seen a Fibonacci sequence before? Like you've seen them talked about or whatever. Okay, it's about 5 of you. A Fibonacci sequence is a non-arithmetic, non-geometric. So it doesn't follow the add something to get the next term. It doesn't follow the, add by a fixed value or multiply by a fixed value like a geometric sequence would. There is a different pattern, but it is actually found commonly in nature. So the pattern starts out like this. I'm going to write one more term. And it will continue. So again, you can see it's not multiplying, right? Because if it were, then 1 times 1 would be 1, but then 1 times 1 is not 2 for the next one, right? That's not good. It's not arithmetic, because if I in order to get from 1 to 1, I'd have to add 0. 1 plus 0 would be 1, but 1 plus 0, again, is not the next number 2. Does anybody, maybe you have seen it before and you want to share the love with everybody else, or maybe you recognize it as you're looking. Do you know what's going on? Abby?
You're adding the number before to the number that you just got. So
Yes.
1 plus 1 is 2.
Yes, so you're exactly right. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. And if we continue through this, we would have the next value, right? 8 plus 13 would be 21. 21 plus 13 would be 34. And of course, the process can continue on indefinitely. There's not a general form, though, right? Like, you can't tell you, like, well, find me the 15th term. Like, you're going to have to do it recursively to find the 15th term if you have this particular sequence. Okay, it feels a little bit like I'm throwing a weird definition in the middle of what we're doing, but we need it in a minute. So let's actually throw this in here where it's placed. A reminder about exponents, a to the n power. If n is a natural number, then a to the nth power is a times a times a dot 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 n times. And for now, by definition, we would say that if n is equal to 0 and the base is not 0, then a to the 0 is equal to 1. Okay, so just having your notes, and then when I need it, I'm going to actually reference back to it. Okay, I'm sure you're ready for me to stop talking and do an example, right? Let's see how all this interplays. So here is an example. It's got lots of parts to it. Each of A and B are going to have us find the I, double I, and triple I. Okay, so I've got 2 examples, but they have multiple parts to their directions. The first thing is usually the easiest. List the 3 terms that come next. Okay, so let's just start in on question A. I've got the sequence 1, 4, 7, 10. What are my next 3 terms? Thank you, Emily. 13, 16, and 19. Okay, so this is like I. That's the answer for I. In fact, I'll put it over here so that I can give myself a little more space. Okay, second one. People are usually pretty good at that part too. Is it geometric or arithmetic? Arithmetic. How come, Elizabeth?
How did you hear me? Because it follows a pattern.
What pattern?
An addition.
You bet. It's arithmetic because we added 3. And if we were asked to, we would be able to say that the common difference is plus 3, right? Didn't ask that specifically on this problem, but that's what the common difference is. All right, 3 is the most interesting. And I will tell you right now that your book shows you how to do number 3 by having you memorize a formula that you then utilize. And I don't really think it's necessary. There's no need to memorize a formula to do this because it's not complicated. So let's actually talk about this because we've already talked about this idea of skip counting and this common differences, right? The common difference here is 3. That's the same as saying it skip counts by 3s, right? I add 3 every time to get the next value. So the sequence that I actually have is a 3n sequence. But what you notice, of course, is that if n is equal to 1, 3 times 1, which is 3, is not my first term. If n is equal to 2, 3 times 2 is 6 is not my first term. Okay, but it is increasing by 3s, but it's not actually like the multiplication table of 3s, right? So I can actually fix that by simply shifting it back 2. So in other words, if I were to do this, right, and I had 3, 6, 9, 12, right? If that were the numbers that I had because I used 3n, how many would I have to take off of that to have the numbers I should be having? How far am I off? I'm off by 2. Every single one of these is too big, isn't it? Right? I don't have 3, I have 1. I don't have 6, I have 4. I don't have 9, I have 7. And I don't have 12, I have 10. So I can compensate by taking 2 off of the formula. And then it does work. 3 times 1 is 3, minus 2 is 1. 3 times 2 is 6, minus 2 is 4. 3 times 3 is 9, minus 2 is 7, and so forth. So I only need to know 2 things in order to create this formula. I need to know the common difference, or what I'm skip counting by. And then I need to know how far off am I. What do I need to add or subtract so it really starts at the right place? Okay? B, same directions. What are the next 3 terms in my sequence? You want to do it, Emily?
2 of them, which is 48 and 96.
Okay, so you got the first 2, 48, 96.
And I think the third one is 192.
You're right.
Oh,
That's it. Good job. It is 192. So, Emily, I'm going to let you answer the second question then as well. What, at least indirectly, what did you do to get those numbers?
it's multiplying by 2.
Okay, so pause there. So, yes, that you're good. You didn't need to pause. You were just keeping going. You multiplied by 2, therefore it was geometric.
Confused on that part. So I said arithmetic on the last one because I thought it was because we were using numbers. But we're always using numbers.
We are always using numbers.
I figured
Yeah.
that, like, mid.
So arithmetic has to do with adding values, and geometric has to do with multiplying by values. That's the difference.
Okay, so because 7 can be multiplied by something to get 10, but 12 can be multiplied by something to get 24, that's not a difference?
It's because here I'm adding 3 to get the next value. Okay? And here I'm multiplying by 2 to get the next value. That's what's happening. I don't know that I've gotten quite all my values in there right, but hopefully it makes sense. Multiply by 2 every time. Okay. So we have the same sort of thing necessary on part 3. We're supposed to create a general formula. And part of our general formula has to do with this idea of what did I multiply by every time. Just like before, what did I add every time? So before I added 3 every time, so it was 3n. And this is where this formula comes into play. If I multiply by something every time and multiply by 2 times 2 times 2 times 2, that's 2 to a power. Right? Because that's what I'm doing. I'm multiplying by 2 to get the next term every time. When I did it with the other one, I'm adding 3 every time. Well, adding the same number every time, plus 3, plus 3, plus 3, that's repeated addition. That's multiplication. So that's why it became 3 times n. It's because repeated addition is multiplication. And repeated multiplication is a power. So my repeated multiplication value, the number I'm multiplying by, or my common ratio, is 2. So it's going to go inside. I'm going to repeatedly do this, so I have to be able to change how many times I'm multiplying by 2 to get whatever value it is. And there's a couple of things that you can just memorize, and then it's not hard to do so. But this is always an exponent of n minus 1. And at the very beginning, we write the number our sequence started with. It was 3. So I'm going to verify with you that it actually worked before we just assume that I know what I'm talking about. Okay, so let's actually check it out. If I have the first one, I put in the number 1. So 1 minus 1 is 0. 2 raised to the 0 power is 1, and 1 times 3 is 3. So it might look a little bit like, well, that's sort of nice and tricky, but that was the number 1, right? And it made 0, that's an exponent. But what if I try one of the others? So let's do it. Let's try the third term. 3 minus 1 is 2. My exponent is 2. 2 squared is 4. And 4 times 3 is 12. Was 12 on my list? Awesome. It's the third one on my list. That's what I was hoping for. Okay, so this equation, this formula, always works the same way. The first term is written first. The common ratio is in the middle. And the power is always n minus 1. So if you want to write that down in words, you could do that. It's the first term times the common ratio, and it's always raised to the n minus 1. Emily?
So did you get the 3 in the exponent because 12 is the third number in the sequence?
Yes, I was using the third term. So I was saying this is term number 1, so this is n equal to 1. This is term number 2, so this is n equal to 2. N represents where we are in our sequence in the list. So this is n equal to 3. This one's n equal to 4. So the benefit in having a formula perspective, a general term or an nth term, is that I can say, well, tell me what the 10th term is in the sequence, and you don't have to find terms, in this case, 6 through 9 to do that. You can simply plug in the number 10 and find the 10th term in the sequence if you have it written that way. Okay? All right, let's do one more example, and then we'll stop for today. Same directions, nth term to find the first 5 terms. I'm sorry, not same directions. Different directions, but same directions for the next 2 problems is what I meant to say. So we're given the nth term formula here. So it's kind of like we're starting with the triple i's that we ended with last time, okay? And we're asked to find the first 5 terms, and we're asked to decide if the sequence is geometric or arithmetic or neither. So we're actually going to put in n equal to 1, n equal to 2, n equal to 3, and so on to find what the sequence actually is. So to start with, if n is equal to 1, I have 5 times 1, which is 5, plus 6 is 11. If n is equal to 2, I have 5 times 2, which is 10, plus 6 is 16. N equals to 3. 3 times 5 is 15, plus 6 is 21. N equal to 4. 4 times 5 is, plus 6 is. Okay, do you see a pattern in the numbers I'm writing down?
Yes.
Do you know what the next one's going to be without actually plugging 5 in?
31.
It's going to be 31. You're right. So this is our pattern. Is it arithmetic or geometric? It's arithmetic. Good job. And why?
Because I'm adding by 5.
Right, because we are adding a number, namely 5, every single time. This is an arithmetic sequence.
So we can never determine if it's arithmetic or geometric until we do
That's a good question, actually. I'm glad you posed it, Gracie. I think it's probably the easiest to see it once you see the numbers written out. However, arithmetic sequences always have this form. A number times n plus or minus a number, and this one has that form. 5n plus 6, a number times n plus or minus some number. So this one's also arithmetic by the form of its general term. And a geometric sequence always has the form where it's exponential like this. A number and a number raised to the n minus 1. So with that on the tip of your mind, hope you can see that B does not look like either of those forms. It doesn't have that structure. So I'm inclined to think, by the way that it looks from the structure of the formula, that it is not arithmetic and is not geometric. We'll find the first 5 numbers to check that out as well. So, oh, and I didn't answer question C. We'll go back to it because it's better to do these together anyway. What is the first term of my sequence if n is equal to 1? 1 squared minus 1, 0. Okay, n equal to 2. 2 squared is 4 minus 1 is 3, right? 3 squared minus 1, 9 gives me 8. 4 squared, 16 minus 1 gives me 15, and 5 squared minus 1 gives me 24. So as you look at these numbers, you can probably tell very quickly that it is neither geometric or arithmetic. Geometric gets ruled out immediately because I can't multiply the 0 by anything and get 3. Like, that's not ever going to happen. And then if I'm thinking about arithmetic, 0 plus 3 gives me 3, but 3 plus 3 doesn't give me the next one, 8, right? So this one is neither. But I'm going to show you something kind of interesting about it after we answer question C's, and that's where we'll end today. Question C on both of these problems is the same question. It wants to know whether or not you're working with inductive reasoning on that problem or deductive reasoning on that problem. Okay? So remember, inductive reasoning is this generalized pattern approach to finding the next values. And then deductive reasoning is where you're given an equation or formula and you're using a set construct, right, to decide what comes next or what the values are. So let's do the previous problem. Is it inductive or deductive reasoning? It is inductive. I'm using pattern recognitions to decide what my next values are. This one, inductive or deductive reasoning? It is deductive reasoning, except for when we actually thought, hey, I think I can see a pattern and there's number 31 popping up. We technically didn't do that with deductive reasoning. But on the ones before we did, right? We plugged in the number 1, we plugged in the number 2 into a given formula to find the next term. I want to show you something very interesting about the sequence that we developed right here. And the reason I mention it is because it will come up on your homework when we get to that point. And you'll be able to see it happen because it's very cool. Okay, so we talked about the fact that it's not arithmetic, and that is true. It's not arithmetic. But what I'd like to do is to take a look at what values I would add to get the next value. For example, this one would be adding 3. But 3 to get to 8, I would have to add 5. What would I have to add to 8 to get 15? And 15 to get 24? 9. Look at those numbers themselves that I'm adding each time. Do you see a pattern in those? Yeah, the pattern of the numbers I'm adding is arithmetic. Because if you looked here and you said, hey, look, this is plus 2. And again, and again. And the reality is, if you wanted to keep building on this sequence without that equation given, right, the formula given, you could do that from here now. Because you recognize that, well, it's not arithmetic, there is a pattern. Now, each of these that I've drawn in here has a name. These are called the first differences. Right? They're the first time we found the differences, how far each of them are apart. So what do you suppose my second line is called? They're the second differences. You're right. And if we still didn't have them all matching at this point, the 2, 2, 2s, we could do it again, and it would be called the third differences, and we could do it again, it would be called the fourth differences. Now, is every pattern going to have this potential? No, of course not. But there are a few examples where that's the pattern going on that they're going to ask you some questions about too. So while it's not arithmetic and it's not geometric, there is an underlying pattern that's happening to create this list of numbers that you can recreate. So for example, on this one, let me move my words here about the vocab now. If you would recognize this plus 9, you would need to know, okay, well, what would I add next? Well, I'd add 11, right? And I'd get 35. And what would I add next? Well, I'd add 13. And I'd get 48. And I could continue going on, right? I could. And if your first differences were not discernible enough to know what do I add every time, you could go to the second differences and say, okay, well, I need to add 2 to 9 to give me the 11. I need to add 2 to the 11 to give me the 13, and so on. Usually if you see it in the first differences like this, you're probably okay, but sometimes it takes to the third differences before they all match. So you might actually need to go a couple layers deep before you see the pattern developing. All right, so we're going to stop for there today because it's a good stopping spot, and we'll pick up with the remainder of this on Friday.